like in Back to the Future. You can have a hovering train. You can even have a hovering car. As you can see, there's many potential applications of this technology. But the problem is, it's hard to implement in real life. Why? Well, one of the reasons is because you need to cool down that superconductor to minus 181 degrees Celsius. But imagine if we could create a superconductor that doesn't need to be cooled down, that could work at normal temperatures and pressures. Well, this might be possible with a quantum computer. And a quantum computer is a fundamentally new type of computer that uses quantum physics. And quantum physics describes how the world works at the most subatomic level, the level of electrons. And if we could basically understand how that superconductor works, how the atoms in it work, then we could potentially create a superconductor that works at normal temperatures and pressures. And so as you can see, this is one of the potential applications of quantum computing. And the reason why I'm talking about it here at this blockchain is because we're going to look at what is the potential of quantum computing, why is it so powerful, and how much progress have we made, and what is that impact on blockchain. So this experiment, I actually saw this experiment about 10 years ago, and that was when I got into quantum computing. So now I'm doing my PhD in physics, specializing in quantum machine learning, but I also do Web3 security stuff on the side. And you've probably heard a lot about quantum computing, and sort of my goal with this is to demystify it so you can understand like what it is and how it's impacting blockchain. So you probably heard that quantum computing could transform our world, including blockchain. So we're going to look at why. First of all, the potential impact it could have. Secondly, the power, why it's so powerful. And then thirdly, how much progress have we made? What's on the horizon and what's now? So let's take a look at this potential. And these potential applications all could be potentially applied to blockchain. So first, we're going to look at something called unstructured search. So to illustrate this, but by the way, when I say classical computer, I'm referring to a normal computer. So that's not a quantum computer. So let's say you had a bag, and you had 4 balls inside the bag, and 3 of them are white, and 1 of them is blue. And you pick out a ball one by one. Well, if you want to find a blue ball, you have to do it up to 4 tries, because there are 4 balls. But on a quantum computer, can anyone guess how long they think it would take? Yeah? 1, yes, you're right. It would just take 1 try on a quantum computer. And this is, in fact, we can generalize it. So on a classical computer, it would take n tries. On a quantum computer, it can take up to square root of n tries. And so this can actually be applied to anything where you have to do some sort of unstructured search. So how do we know this is possible? Well, this is because of a quantum algorithm called Grover's algorithm. And there's a guy called Grover who created this algorithm several years ago. And quantum computing, as you can see, can speed up certain processes. It can speed up certain algorithms. And there's one algorithm that it can speed up, which has a big impact on the blockchain. So let's say I give your computer the number 15, and I say, what 2 numbers must you multiply? Your computer says, oh, that's extremely easy, 5 and 3. But what happens if I give it the 617-digit number, and I say, find me the 2 numbers? Obviously, your computer can't do that. It might just blow up, because it's estimated it could take up to 1 billion years using the best-known classical algorithms just to find out what those 2 numbers are. And anyone guess, like, on an ideal quantum computer, how long you think it could take? Shout out a number. 1 second? 1 year? Okay. So 1 minute, okay. So it's estimated it could take about 100 seconds on a quantum computer to find out what those 2 numbers are. And how do we know this is possible? Well, you may have heard of Shor's algorithm. So this was created by a professor called Peter Shor, who was at MIT. He created this algorithm in 1994. And as you know, or may know, this has a big impact on internet, Web 2 and Web 3, because this is what keeps encryption secure. So basically, as long as those 2 numbers are like your private key, the as long as you can't know those private keys, those two numbers, you're secure. But with a quantum computer, you can essentially decrypt that data. So now the question is, should we be worried? Well, they are, in true quantum fashion, yes and no. So one reason we should be worried is because of this thing called SNDL. Can anyone guess what it means? I don't know if anyone knows this. It's a bit of a stretch. Okay, I'll give you a bit of a clue. So S, now, D, later. No one's heard of this? Okay, the idea is, I actually didn't write it. It's store now, decrypt later. So the idea is that you store encrypted data now, even though you can't decrypt it now. When we have a quantum computer, then you would actually be able to decrypt it. And this is obviously a big problem because essentially any data that's encrypted now and in the past is essentially open. So that's why it's sort of essential to start encrypting data with new encryption methods that are safe against quantum computers. But the thing is, people are coming up with solutions to this problem. So there's a whole field called post-quantum cryptography, and the idea is to create new cryptographic schemes that are safe against quantum computers. And you may have heard of the NIST, which is the National Institute of Standards and Technology. They actually had like a contest for people to sort of submit new algorithms, and they would recommend these new schemes. So yeah, but the problem is that apparently it took about 20 years for people just to deploy the modern cryptography infrastructure. So it's estimated it could take, maybe a decade just to be able to replace all of our encryption systems. And to give you an idea, it's estimated we could have a quantum computer that could break encryption in about 10 to 20 years. So there's sort of a race going on, and it's sort of essential that we start doing these things now. But later in the talk, you'll see sort of how far along we are and sort of what the quantum computers were built today and the capabilities of them. So that's sort of one potential application which has a huge impact on Web3. And the others I'm going to sort of brush over, but a big one is understanding nature. So everything around us is made of atoms and molecules, and they all follow the laws of quantum physics. So a quantum computer can basically simulate anything in nature more efficiently than our normal computers. So that could impact medicine, materials, energy, and of course these would all have an impact on Web3 as well. And then, of course, you can't be anywhere without mentioning machine learning or AI. Quantum computers can advance, potentially, artificial intelligence. And if you are familiar with machine learning, it's just basically a bunch of vectors and matrices in a high-dimensional space. And that's actually quantum computing. If you study the mathematics of it, it is a bunch of vectors and matrices in high-dimensional space. So there is a field called quantum machine learning, and that's actually what my PhD is looking at. So you can see that quantum computing can have an impact across a variety of different areas, which will all affect blockchain. So things that are kind of practically impossible today could be made possible with quantum computers in a variety of industries. And I'm on a council for the World Economic Forum, and we published this report called The State of Quantum Computing. So if you're interested in reading more about the applications and its impact, you're welcome to take a look at that report. So now you're probably wondering, okay, why is it actually able to do all of this? Like, sort of what's the power behind quantum computing? Why can it break encryption? So we're going to take a look a bit at the fundamentals. So first of all, we have the quantum bit. So let's say you're typing up an email to your friend. You say, hey, smiley face. Well, you may speak English, but your computer speaks binary, of course. So everything you do is translated to these sequence of zeros and ones. And so this is sort of the bit that we're looking at. The bit. So I like to use a donut analogy. So imagine you have a donut, you have a plain side, it's 0, a frosted side, it's 1. Now, in a quantum computer, we call them quantum bits, also known as qubits, and they can actually be 0 and 1, but they have something special. They have access to quantum physics, which means it can behave in a quantum way. So in particular, it can be in a superposition, which I like to think of like a spinning donut. Now, it's sort of a combination of 0 and 1. So why is superposition powerful? Well, let's imagine you have a donut box and you open it up. Inside, you see two donuts. Either you see 0, 0, or you see 0, 1, 1, 0, or 1, 1. But what if this were a quantum donut box? You'd open it up and you'd see them both spinning. And now, essentially, you see all of these combinations sort of simultaneously. And so the quantum computer, it can actually process on these combinations, all of them. So to give you an idea of how powerful this is, let's say you had 300 qubits. How many classical bits would you need to represent 300 qubits? In other words, how many combinations are there with 300 qubits? Anyone want to shout an answer? A lot is true, but not quite precise enough. 2 to the power of 300. Is that what you said? Yeah, that's correct. So 2 to the power of 300, which is roughly 10 to the power of 90. So that's this number. So that's 90 zeros. So you need 10 to the power of 90 classical bits to represent 300 qubits. And actually 10 to the power of 90 is estimated, it's more than the number of estimated atoms in the universe. So you can see that's where the power of, like, one of the powers of quantum computing comes from, is this ability to be in superposition and sort of have all of these combinations with just a few quantum bits. So yeah, you can generalize this, so n qubits, 2 to the power of n classical bits. So, but how do we actually process on the quantum computer? How do we implement an algorithm such as the Shor's algorithm, which can break encryption? Well, we use something called quantum gates. So logic gates, you have 0, you put it through a NOT gate, it ends up being 1. Well, this is how you basically build the classical computer. And in quantum computers, we have something similar called quantum gates. So they change how the qubits behave. So, for example, we have this NOT gate. We put it 0, it goes through the NOT gate, and it ends up flipping it to a 1. So that's sort of the logic of the quantum computer there. But we have something more special. For example, we have something called the Hadamard gate. So it's 0, we put it through the Hadamard gate, and now it ends up spinning. So now this puts it into superposition. So, and then basically we can take these quantum gates, and then we can put them together to create quantum circuits. So I like to think of baking a cake as a little analogy. So if you're baking a cake, you have a recipe. It tells you a set of instructions on how to use the tools you have, such as a whisk, to change the ingredients, such as eggs, to end up getting your cake. But with a quantum computer, you have a quantum algorithm, a set of instructions, tells you how to use the tools you have, the quantum gates, to change the qubits, so you end up getting the solution that you want. So finally, you can actually program quantum computers. So yeah, I'll go over this, but anyone can access a quantum computer, which is something that people don't realize, but people have built quantum computers. For example, IBM has them, and you can access it through the cloud. And you can program the quantum computer using the gates. So this is something called the IBM quantum experience. You have these like lines, and these correspond to each qubit. And then you have the tools you have. So these are the quantum gates, and you can basically drag and drop. So essentially, you could do Shor's algorithm on a very small number just by dragging and dropping these gates with these qubits. And then, yeah, you can also write it in Python, for example. So, okay, this is a little example of writing it in Python. And I'm trying to quick it up. So yeah, so basically here you say apply this gate to the quantum circuit. So yeah, there are a bunch of cool things that you can do, but the whole idea is that you use quantum effects to solve problems leading to new results. So finally, sort of how much progress have we made, and sort of where are we in regards to it, like breaking encryption? Well, in order to understand that, we need to understand the hardware. So basically, in classical computers, you have these transistors, right, which block and allow the flow of electrons, which act as zeros and ones. Well, in quantum computers, we actually have many different ways of building a quantum computer. So, for example, you can use superconductors, trapped ions, photons, which is light, and even diamonds. And the point is there actually isn't one way to build a quantum computer. There's many ways. So we're not at the level of the transistor, which is like just taken off. And people are trying to explore these new ways. And here's like a little video of me actually going to a quantum computing lab in Oxford where I'm doing my PhD. So this is sort of like a look at the actual quantum computer. So this is the fridge, which basically cools down the system in order for it to work. And you need to cool it down because it uses superconductors. And when you basically, so this is sort of the inside of the fridge. And when you run something on the quantum computer, let's say I'm typing something using the IBM Quantum Experience. So this is actually this is the quantum chip. And you can actually see the 4 qubits with your eyes. And they have a familiar shape. They have the shape of a donut. So qubits are actually equivalent to these donuts. And you can have actually different shapes of these qubits. But the idea is that when you run something on the quantum computer, you actually, it basically sends the instructions through the cloud to this device, and then it applies the operations to the quantum computer. So for example, it would apply the, so it goes through all these wires through the cloud, and applies the operation. So in this case, we put it into superposition, and then it sends it back to our result. So the idea is, I showed you there 4 qubits, but in order to actually break encryption, you need millions of qubits. So you can see just with that chip, you need millions of those qubits to break encryption. And the largest quantum computer we have today is around 400 qubits. So that sort of gives you an idea of the progress. And there's a huge challenge with building these quantum computers, just that they're so fragile. Like, for example, if you have a spinning donut, eventually it would stop spinning. And it's similar in a quantum computer. The qubits lose their quantum effects. They lose their superposition, which is a big challenge. So that's why it's sort of hard to build quantum computers. And here's sort of a graph to show, like, if you were to control 2 qubits, these are all the physics experiments that you need to do. So 1 dot equals 1 physics experiment. And the guy who presented this, I asked him for the slide. He showed me that was his PhD. So I don't know, as a PhD student, is that encouraging or discouraging? But as you can see, it's extremely complicated to build, and that's why it's taking a long time to build something with millions of qubits. But despite that, we've made a lot of progress. So there was a big result in 2019, which you may have heard of, called quantum supremacy. So this was basically the first time that a quantum computer actually outperformed a classical computer at a particular task. So a quantum computer, it took 200 seconds, and they estimated it would take 10,000 years on a supercomputer. And that was the first example of a real problem that could be solved exponentially, like faster, on a quantum computer. And so now is sort of what's next. Next is sort of this idea of actually doing something practical with a quantum computer, which we call quantum advantage. So hardware providers are going to build more resources. So they're going to build quantum computers with more qubits, getting towards millions of qubits. But also algorithm developers are trying to use fewer resources. So they're trying to develop algorithms that don't require as many qubits. So it's possible that someone creates an algorithm that only needs to use a few qubits that could break encryption, and that would be even a bigger problem. But it's probably unlikely, but it's possible. So as you can see, if we get to that point, then we can get quantum applications. And sort of, this is sort of the things that is left to do in quantum, is like build more applications, more theory, more hardware, and more systems around it. So you can see that this is sort of, we talked about the potential, the power, and the progress that is going to be made with quantum computing. And it's only a matter of time until it turns our world upside down. Yeah, that's it. Thank you. Yeah. Right, so that's related to the encryption question. Oh yeah, sorry.
Yeah, I mean, the really, like, the 5-year, like, explain like I'm 5 question is, when are the encryption algorithms that run the entire cryptocurrency ecosystem, whether it's at the L1 layer, at the app layer?
Yeah.
when are they going to be broken by quantum?
Right. So yeah, I touched about that in the talk. So that's the Shor's algorithm, which can break the encryption, and it's estimated you need millions of qubits to do that. We at the moment have about 400 qubits, and it's estimated it could take about 10 to 20 years before we get to, millions of qubits. But obviously that is speculative. Who knows? It could be faster or shorter. Yeah.
Hey, great talk. I was wondering, what was this experiment about where the quantum computer actually, for the first time, beat the classical or supercomputer?
Yeah. So it was sort of a made-up problem. So it's not a useful problem, but basically they actually just simulated a random quantum circuit. So it was basically a random mathematical problem that has no use case apparently.
Gotcha.
So,
fair enough. Thanks.
So, hi. So, I think this quantum supremacy problem which you mentioned, actually quite soon after that, it was simulated on a classical machine.
Yeah.
And not in 10,000 years, but in a few months.
Yeah.
So this claim of the quantum supremacy, I believe by the Google, was kind of refuted with the classical machine.
Yeah, so after the quantum supremacy experiment, I was going to go into that, but this is a short time. But yeah, there were claims that it would actually take less time, so like a few months. But the principle, I think, is the same, even if it was like 10,000 years versus a few months, that the quantum computer still was faster than the classical computer. And also the thing is, if you add just one more qubit, then it basically blows it out of the park, because with one more qubit, you have exponentially more power. So it's a bit hard to verify sometimes if a quantum computer has advantage, because you can always maybe find something classically that does better. And so IBM published something, but they didn't actually run it. But yeah, I think the principle stays the same, but the numbers are up for debate.
So also with the papers which questioned the way the statistical analysis was done by the IBM as well.
Yeah.
And I think they find some flaws again, basically, in the statistical analysis. It was a bit biased towards, the better results.
So IBM did come out with. They said if you use all of these all of this hard drive, memory and all this stuff, then you could do it. But it was, I don't know if I don't think they actually performed it. But so.
Thank you.
But
Very nice talk.
Yeah, thank you. Thank you.